Vijayan sir, you can start, sir. Vijayan, we can start.
Yes, yes. Good morning to everyone joined here. Today we are in 5th day of 2 weeks online FDP on advances in composite materials, manufacturing processes, and optimization techniques. We are very happy for the overwhelming response from the participants and their cooperation. In today's first session, we have Dr.N. Senthilkumar sir with us to deliver a speech on machining simulation. He completed his bachelor's degree in mechanical engineering from Government College of Engineering, Salem, and he completed his master's degree in manufacturing with the gold medal from Madras Institute of Technology, Chennai, and he received a doctorate degree from Anna University, Chennai. He published more than 80 research articles on various international journals and conferences. He is a reviewer for 30 international journals and including Elsevier, Springer, Sage Publications, and he is also acting as an editorial member for various international journals. He presently working as a professor in Department of Mechanical Engineering, Saveetha Group of Institutions, Chennai. Now, I would like to invite Dr. N. Senthilkumar sir, Professor Mechanical Engineering, Government, Saveetha Group of Institutions, to address the gathering. Sir, please, sir.
So, good morning to everyone. First and foremost, I have to thank Dr. R. Karthikeyan sir, Head of the Department of Mechanical Engineering, Ahmad, and my beloved friend, Dr. Chalam, and Professor Vijayan for this opportunity. And today we are going to look into the simulation of machining process. So, this today's session, I will be splitting into two sections. First, we will see some of the basics of the simulation process through the PPTs, and in the second half, we will have a hands-on training session how to perform a simulation study in a software. Okay, with a small introduction, we will move on to the presentation. So, simulation of machining process. Okay, so this is the general simulation. So, here you can see there are two categories where a workpiece will be stationary or the tool will be moving, or this tool will be stationary and the workpiece will be moving. There are two conditions in which the machining simulation can be performed. Okay, so the machining simulation can also be performed in 2 dimensions and also in the 3 dimensions. So on the left side you can see an image. So that is the tool, workpiece and the chip. So that is a 3-dimensional. On the right side you can see a chip, tool and a workpiece, and that is the 2-dimensional one. So that's the difference. A realistic model can be obtained only with the 3D models, but the complexity of the process will be higher, and also it takes higher computational times than that of the 2-dimensional machining simulations. Okay. So before going into the elaborate study of this simulation of machining process, we should know some of the basics pertaining to this simulation. Okay. So these simulation and all will be coming under the CAE, Computer-Aided Engineering, because nowadays we are going to use computers in engineering analysis. For performing critical and complex tasks. Okay, that's why we have got the name as computer-aided engineering, because the computers are going to aid. So in this computer-aided engineering, we have different categories, which we will be having the FEA, CFD, multi-body dynamics, likewise. The finite element study is basically dividing the component into small finite elements. In computational fluid dynamics, we will be dealing along with the heat transfer, mass transfers, likewise. And in multi-body dynamics, we will be doing with the the vibration analysis, the crashing of automobiles, likewise. Okay. So in finite element analysis, we will be using the finite element methods. So in which we are going to discretize. We are going to discretize the parts into small elements. So the solution for a particular element will be moved towards the solution for the entire domain space. Okay. So in all these FEA, we'll be using partial differential equations. Okay, the people who are, because we are going to have the FEA in all our studies nowadays. So everyone will be aware of that the partial differential equation is of that much importance in engineering. Okay, that's why there is a separate subject called as partial differential equations whenever we go on to a specialization 1. So what is meant by modeling and what is meant by simulation? These two are different words. Okay, so a model is nothing but abstract. Okay, you can know, you are going to write a paper, you should write the abstract. That is the essence of a paper. So similarly, the model is only a abstract that is being defined, that is really equivalent to the real conditions. Right? The real conditions is nothing but we are going to have a product and that may be having some key properties and characteristics. For example, the material properties, the thermal properties, likewise, and also the characteristics, how it is going to perform. Okay, so that and all we have to put it in a real-time model by using the computer systems. Okay, so for what purpose we are going to develop this model? Okay, so since we have seen that this model is a computer-based one, but it is equivalent, realistic, like a real system. It is a realistic system. It is like a realistic system. So for what purpose we are going to use this realistic system? The first most important thing is for critical investigation. For critical investigation only, we are going to develop these models. And then we are going to use it for the demonstration purposes. So I doesn't know how a turning operation is going to work, how a drilling operation is going to work, how a forming operation is going to work. Now I want to visualize things. What are the metal deformations that is taking place? How the shearing action is taking place? That and all we cannot visualize in the real-time conditions. So for the demonstration purposes, we will be using this simulation studies. From this model, we can easily visualize how the shearing action is taking, how the metal deformation is going to take place. Likewise. So for this purpose only, we are going to develop a model. If I am going to study these things in realistic conditions, then the expense will be very, very high. And also, in some of the cases, it is not at all possible. You can see a turning process. You can see the cutting tool is going to be in contact with the workpiece at a very, very, very small area. In that place, high shearing is going to occur. High shear is going to occur. Will it be able to see that? No, it is not at all possible. So that and all we can visualize properly through this simulation studies. So that's why we are going to develop a model. And also, we are going to, while developing the model, we are going to provide some general statements or whatever it is called as assumptions. Okay, about what type of element that we are going to select. Whether it is a tetrahedron element, a triangular element, a rectangular element. Okay, so likewise, we are going to provide statements about what type of element that we are going to take, what kind of structure that it is going to have, right? And how it is going to behave in a realistic manner, in a real-time system, how it is going to behave. So these and all we are going to incorporate into the model. We are going to incorporate into the model. Okay, so you know the best FEA software is the ANSYS. In that also we are going to provide these kinds of statements. Okay, for example, I'll tell one statement, whether we are going to carry out the machining simulation in transient condition or in a steady state condition. Right, we have to measure the values, we have to determine the values once the machining process has attained the steady state condition. Initially, the steady state conditions will not be attained. So first we have to carry out the simulation in the transient conditions, and after some time only we have to convert that into a steady state condition. So two parts will be there. First one is the transient conditions, and then we have to move on to the steady state condition. So like this, we have to provide the statements, the assumptions, what we are going to do. Then, what is meant by simulation? Simulation is nothing but an imitation. So what we are going to do in a turning process? We are going to use a cutting tool that is sharp enough and it is also harder than that of the workpiece. So this is the basic condition of a tool. It should be sharp and it should be harder than the workpiece so that it will remove some material from the workpiece. So this is the real-time condition. So the same condition, if I am going to imitate by using a computer system, then it is called as a simulation. And that process is being carried out on the developed model. It's carried out on a developed model. I will tell another simulations, not only this, simulated annealing. You can see simulated annealing, the artificial neural network. So these are all going to imitate. In simulated annealing, we are going to imitate the annealing process, that is the heat treatment process for optimization. In ANN, artificial neural network, we are going to imitate the behavior of our own human neural network system, so that we are going to use it for the prediction purposes. So simulation is nothing but the imitating the behavior of the realistic condition through the developed model, right? Then we are going to study, we are going to simulate whatever it is, but what is the need of that? So initially we have seen the model is being developed for critical investigations and also for demonstration purposes Now what is the need of this model? So that is very, very important. Without a need, we cannot do anything. Okay. So in any design process, the first step is the recognition of need. Without need, there is no necessity at all. Then what is the need for a machining model? Right. The important dependent variables. So we call the two types of variables, dependent and independent variables. The inputs are the independent variables and the outputs are the dependent variables. So the important machining parameters, that is the dependent variables, are the cutting forces. Okay, if it is 2-dimensional, Fx, Fy. If it is a 3-dimensional, then we will move on to Fx, Fy and Fz in turning. If I am going to move it on to a drilling process, then thrust force and torque. So these are the cutting forces that is going to act. Okay. So measuring these forces will tell us how much amount of force is being required to shear that material. Okay. Then what is the temperature? There are two types of temperatures, the interface temperature and the chip temperature. The temperature at the interfaces has to be as low as possible, because the temperature is getting rising because of the higher frictions. So measuring the temperature is very, very important. Then the chip morphologies. There are different types of chips: continuous chips, segmented chips, continuous chips with the built-up edges, likewise. So all these things will have a realistic control about what kind of material that we are going to select and what is our machining parameters, that is cutting speed, field rate, depth of cut. So these two, the machining parameters put together with the type of material, will decide the chip morphologies. Then stresses and strains. What is the stress that is going to act during the shearing process? How much amount of stress is going to act on the cutting tool? How much amount of stress is going to act on the workpiece? So that and all we can study. Why we have to study? In real time, we are going to measure it using expensive equipments. So the Kistler dynamometer, that is the perfect one, which uses a piezoelectric material, is used for measuring the cutting forces. Piezoelectric, that is Kistler. So that is available in Anna University, then Karunya, then Satyabama, likewise. SRM also they are having. It is around 35 lakhs. Right? So for the how much amount of cutting forces that is going to really occur, that can be studied before going into the real-time experiment by using this simulation studies. So if this is the case, higher cutting forces are available, then our intention is to reduce that cutting forces. Our intention is to reduce that cutting force. So which can be done before going for the real-time experiments. So before going for any real-time experiments, so the cutting forces, the temperatures, the chip morphologies can be extensively studied using these machining models. That's why the simulation plays a very, very important role. Apart from the demonstration or critical examination, the simulation studies are very, very important. Then I am having a material, I want to turn it or I want to drill it. Okay, now I doesn't know what is the optimum condition. The optimum condition is which produces the best result. I want a good geometrical tolerance, but at the same time, I need a lesser cutting forces, a lesser temperature, whatever it is. So for this, I have to go on with a trial and error approach. I have to change my cutting speed, feed rate, depth of rate, okay, as a trial and error, and then I am going to perform the studies. So which is a costlier and time consuming, and also it is very laborious, because in real-time conditions, the manpower that is being utilized is going to be higher whenever we are going with the trial and error approach. Because once you are going to use a cutting tool for an experiment, for the next experiment, we should not use the same cutting tool, because during one study, there will be some wear on the cutting tool. If I'm going to use the same cutting tool, then the cutting forces, the temperatures will be varying. That's why in investigational studies, we'll be using different cutting edges for each and every experiment. That's why it is a most laborious and also costlier. Right? So this is the main important thing. Okay. With the modeling, that is by using the simulation models, the resources are spared. That is, I am going to prevent the usage of resources, the manpower, the equipment, the electrical power that is going to use, the cutting tool that is being used, the workpiece material that is going to be used will be spared. And also we are going to obtain a optimum condition. By using this, we are not going to use except the computer, so the cost is also being reduced. That's why we are going for these machining models. So what are the benefits that we will be having from the machining model? So it drastically reduces the experimental work. It drastically reduces the experimental work, because while I'm going to directly, if I'm going to do that, then I'm not able to reduce the cutting forces, temperatures, because this cutting forces, temperature will always depend upon the tool material that we are going to use, the workpiece material that we are going to use, then the machining parameters that we are going to select. If it is a hardened steel, then using a HSS or a uncoated cemented carbide will not be fetching you good results. So in that cases, we have to move on to a cermet tools or PCDs or CBM. Likewise, if I'm going to go for this, then the cutting forces will be really reduced. So this modeling reduces the experimental work. Then the main important thing is understanding the fundamental issues or fundamental concepts of machining. Okay, so that's why we call it as it is specifically useful. Apart from the critical investigation, it is specifically useful for demonstration purposes, because the fundamental issues has to be understood well. The basic concepts of machining theory has to be well understood before going for any research. So by using the simulation models, it is particularly important. Okay, and it is particularly able to understand the concept in a really good manner, because understanding is the next best thing to the ability to predict. If you understand the basic concepts well, then we are at the edge of predicting things really in a nice manner. Right. So once we understand the basic concepts, then it acts as a feedback loop for machining research. So that is what I am telling in the previous point. Because for research, the understanding of basic concepts is very, very vital, and that is possible with these machining models. Then, even though it has some advantages, it also has some disadvantages. Sorry, we should not use the word disadvantages, but it is the difficulties. There is no disadvantage of going for any simulation models. It is only the difficulties that we will be facing in the simulation studies. Then what are the difficulties we will be facing? Right. So rather than drawbacks, it is the difficulties. Okay. In doing modeling, if I am going to consider too many variables, right, then what happens? The complexity of the problem will be higher. What happens when I am going to consider less number of variables? The intention will not be resolved. The intention will not be resolved if I am going to choose less number of variables. If I am going to choose a higher number of variables, then the complexity of the problem will be higher. So a trade-off has to be made between these things. That's why the basic understanding of the concept is very, very essential. So we have lots and lots of machining operations, right? So even though it has some similarities, it is not the one and the same. For example, take a turning process, take a drilling process, take a milling process. All these processes are metal removal process, which uses a cutting tool. Okay, the difference between turning and drilling is turning uses a single point cutting tool and drilling uses a multi-point cutting tool. The tool is stationary in this case of turning and the workpiece is stationary in the case of drilling. So in both the cases, the material will be removed by pure shearing action. So even though similarities exist, these two processes are different. Right? So developing a universal model is not a realistic one. So that is the one type of difficulty that we are going to face. So developing a universal model is not possible for studying the simulation of machining process. Right? So normally we will be going on with the orthogonal cutting process. There are two types of cutting process, oblique and orthogonal. And normally we will be interested in orthogonal machining process and also shear plane models. But even these two systems are of criticism. Even though we are going to use this, is even nowadays it is in criticism. So which is the best model that we are going to find? Right. Because the one more difficulty is, so machining is still one of the least understood machining process. Why? How the shearing action is taking place. Like the piston model we are going to study. So shearing takes place along the shear zone, right? Like the stack of cords, the piston model. But even though it is least understood, okay, so that is one more difficulties. So this is the point that I have told. So in turning, you can see the point of the cutting tool will be touching the workpiece. You can see we have only a small area where the cutting tool will be in contact with the workpieces. At that small area, very large strains and stresses will be acting. Then only the material will be sheared off. Then only the material will be sheared off. So at the small point, how much stress and strains are going to act. So that and all, it is making it very difficult to understand. That is the one more difficulty that we will be facing. Then chip forming mechanisms. So as I told her, the chip is removed from the workpiece because of the action of the cutting tool purely through the shearing action. Right? So the chip formation is really complex. Right? And the associated models is also complex. So the final we can see chip formation models, then friction models and all we will be seeing at the last. Okay, because not a single model is available. We have different models. So for your work, which is the best suitable one that we have to select. Okay, there are different models from which we can select. For our work, which is suitable, we have to select. Only from the doing the literature. From studying the previous literatures, we can adjust them. We can understand that. So you can see in a design process, while designing a helical spring or designing a coupling, we have some assumptions, or even in a design of some machine elements, we can use some assumptions. But over assumptions, considering higher assumptions, make the problem oversimplification, which is also a problem, which is also a difficulty. So considering so many assumptions, okay, will oversimplify the problem, which is also the difficulty that what we will be facing. Right? So if we are going to consider higher assumptions, then the obtained results will be inaccurate. We are not able to predict the real behavior of the system because we have assumed a higher number of conditions. So that is the one more difficulty that we will be facing. Then finally, the properties that what we are going to provide and the machining parameters what we are going to consider will make the system more complex. Right? Tool properties. What are the tool properties? First one is the material. Then what is the rack angle? What is the relief angle? What is the nose radius? Okay, what is the approach angle? What is the approach angle? That what we will be having. So that is the tool properties. Then workpieces. What is the material that the workpiece is going to be made up of? Okay, whether it is a low carbon steel, high carbon steel, or medium carbon steel, or if it is a composite material, then the complexity will be more. Okay, so the variation of workpieces. Then apart from this, what is the machining parameters that we are going to consider? The cutting speed, feed rate, depth of cut. Apart from this, we can also have whether we will be using cutting fluids or not, whether it is the wet machining or dry machining, or MQL, minimum quantity lubrication, or we are going with the cryogenic machining. So these parameters will increase the complexity of the real-time conditions. So these and all we can use during the simulation process also. Then, how to select a model? Because the model that what we are going to develop or select will influence the output responses. So selecting the perfect model for your study is very, very important. So what is model? The workpiece model, the flow stress equation, the friction model, the tool wear model. Right? So these are all the models that what we are speaking about. Okay, the flow stress equation for the material model, then friction model, then wear model. So these are the different models. Okay. So how we are going to select the models? So depending upon the model only, the output will be whether it is reliable or not, we can decide. Right? So the selected model will provide a reliable answer to the output. Otherwise, the model what we have selected is a pure waste. And the computational time that what we have waited for is also a waste. So there are 5 generic categories of modeling techniques that is really available in this case. So first one is the empirical modeling, then analytical modeling, then mechanistic modeling, then numerical modeling, and then artificial intelligence modeling. So these and all we are going to have. So analytical model uses previous developed equations to define the model. Then the empirical model uses the experimental data to build that model. Empirical model uses the experimental data to develop this model. Likewise, different categories are different methods. So you can you all know this very well. So I am skipping this out. Right. So there are 2 types of models. One is simple models, and the other one is the complex model. Simple models require lesser number of input data, whereas complex model require higher number of input data. Then what is the difference between these two? The simple models require less computational time, and the complex model require more computational time. The results obtained from the simple model is not reliable, or it is not that much accurate, It is not that much accurate, but the results from the complex models will be more accurate than that of the simple models. Okay, right. So in the earlier days, in 1980s or 1975s, while doing the simulation studies, the tool wear was the utmost importance. So more and more importance was given to the tool wear. Okay, but nowadays we are going to move from the tool wear. So along with the tool wear, we are also studying we are doing investigations on the cutting forces, the temperatures, what type of chip is being produced. Okay, the geometrical accuracies. For example, the cylindricity, circularity. Okay, so these and all we are interested on, and also this roughness of the machined surface. Okay, the roughness of the machined surface. So this and all we are more interested on. Okay, so that is one more important thing in selecting this model. And then apart from normal machining, we are also interested in high-speed machining. Okay, in high-speed machining, the workpieces will be rotated at very high speeds. Okay, so apart from this, we are also environmentally conscious. That means we are going to move from the flood cooling. We are going to move from the flood cooling to dry machining, or we also call it as a hard machining. Dry machining, that is no coolant will be used in dry machining, or we will be using the MQL, minimum quantity lubrication, or mist cooling, MIST, mist cooling also we will be using. And nowadays we are going to move towards cryogenic machining. We are also going to move towards cryogenic machining also. So first, initially the simulation studies are of much giving much importance to tool wear only. But now you can see what are the different categories of machining studies. We can do that in simulation. Okay, that is the development of the simulation studies. So even though you select some specific models for our study, some models will tend to fail. So why a model will fail? So that is the first question that arises, right? So a model fails if it doesn't predict accurately, if it doesn't predict the cutting forces accurately, predict the temperatures accurately. Why? Because the model that what we have developed, what we have selected, the flow stress equations, or the wear model, or the friction model, what we have selected during our initial stages of simulation, if it is not good, then the prediction values will be inaccurate. Right? Right? The models fail if it is not so simple. Okay. Previously, we have told that two differences between a simple model and a complex model. A simple model requires less computational time, but a complex model requires higher computational time. But complex models are more accurate than that of the simple models. But we require fast results. If it is a simulation is running for 3 days or 4 days, then we cannot wait until that. So what models, even though we develop models, it should be as simple as possible. It should be as simple as possible so that the computational time will be reduced. Then many models fails because of incomplete input data. First one is incomplete input data, or omitting some of the critical factors, The most important critical factors in turning process is the cutting speed, feed rate, and depth of cut. If in a study, if I am going to omit that feed rate, whether all the answers that we have obtained is correct? No, because we are omitting the critical factor of feed rate. So a model tend to fail if some of the critical input parameters are omitted, right? Then we move on to the finite element method. So it is the most flexible and versatile method. I move a little bit fast because everyone knows this concept. Okay. So the FEM, the finite element method is made up of small interconnected sub-regions. Okay, so that is called as elements, and the solution will be obtained for that element, that is piecewise approximation. So the solution will be obtained for that element through the piecewise approximation, and then it will be transferred to the whole domain, okay, by integrating. So this is the, on left side you can see the tool holder that we will be using in CNC machines, the tool holder. Then you can see the black colored one, no? So that is the cutting insert. So this is a triangular insert that what we are using. This triangular insert can be used 6 times, because at the top we have 3 cutting edges and at the bottom we have 3 cutting edges. So this cutting insert is like a 6 cutting tool, because it has 6 cutting edges. So that is the advantage of going with this triangular shaped inserts. Okay. So this is how we are going to discretize. This is the tool and this is the workpiece. So this is a 3-dimensional models. You can see as a 2D, you can see this is a square shaped element, but here this is a triangular shaped element. Actually in 3D it is a tetrahedron. It is a tetrahedron that is being joined at the edges. Okay, so initially for this particular element, a piecewise approximation can be done, and from this, for this total domain, we are going to provide the outputs. Okay, so that is the importance of FEM. So the unknown state variables, for example, the stress, strain, in the temperatures, the cutting forces, that is the unknown state variables, are solved at a discrete number of points, at many points, right? Then from that, we are going to move it towards the total domain, right? So the total domain is being discretized. Discretization is nothing but splitting that into elements. The process of dividing the problem domain into equivalent system of small domains. That is, the small elements will also represent the solution. Okay, that is called as discretization. So once the problem domain is discretized, so solutions can be obtained for the particular element, and from the particular element we can we can get the solution for the entire problem domain. Okay, so the domain-wise solutions can be combined together to obtain the solutions for the entire domain. So this and all you know it very well, so that's why I'm moving it fast, right? So what is called as nodes and what is called as elements? These discrete points are called as nodes. Here you can see, so this is called as, so the star and all, no? So this is called as nodes, and this is called as a element, a triangular element. Okay, so this is called as a triangular element. So, and this is called as a node. Okay, so elements and nodes that is put together will constitute the mesh. Okay, so meshing takes place, how it is being connected with the other elements. So the fineness of the mesh increases the accuracy and also the computational time. If the mesh size is higher, the computational time will be less and the accuracy will also be less. If the fineness of the mesh is higher, then higher computational time along with the accurate results. Okay. So this is how we are going to have the basic idea of them. So you can see the primary nodes and the interior nodes, and this is the discretization of it. This is like a doom. Okay, so this is the triangular element. So after deformation, you can see. So these rose colored dots, no, that is the nodes which will be connected to the subsequent nodes. Which will be connected to the subsequent nodes. So here we can see the elements that we normally use it for the 2-dimensional as well as for the 3-dimensional studies. For 2-dimensional studies, we will be having the triangular, that is 3-noded, 6-noded, then quadrangle, and then 8-node quadrangle. So normally tetrahedron, that is number of nodes. You can see how many nodes. If I increase the nodes, then the accuracy level will be higher. Okay. So the computational model using FEM. So now we are entering into the simulation, how we are going to develop a. So I'll be moving a little bit fast because the time is very, very less, because the simulation studies will take minimum of 20 to 30 minutes. Okay. The first one is modeling, then second is meshing, then specification of material property, and then boundary conditions likewise. So modeling of the geometry, then meshing, then defining the material properties, then boundary conditions, the loading conditions and all we are going to provide. Right? So the different types of models is the lower and upper bound solutions we will be having, then shear plane models we will be having, then slip line field models. So this and all we can see it in the manufacturing technology too itself. So what are the different models? What it is going to tell? So that and all we are going to include. Then shear zone models. So these are the 4 models that we are interested in developing a model. Okay. So the lower bound solutions employ the principle of maximum work, right? Because once it is going to deform, it dissipates energy. Okay, because deformation is being carried out with the dissipation of energy only. Energy can neither be created nor be destroyed, but energy gained is equal to energy lost. So the dissipation of energy, that is subsequent to the next elements. Okay. So this and all I will move faster. So you can see the shear plane model is provided by Ernst and Mech. In shear plane model, we are going to have a Pispanian chord model, that is stack of chords, like a playing chords. So by layer, the metal will be removed, okay, along the shear plane, right? So these are the things that is being assumed. The chip is straight. Actually, whether the chip is straight, no, it is curled. But we are going to make it a simple model. Then for that only we are going to assume that it is the chip is straight. So and also the chip is assumed to be rigid body. The rigid body doesn't deform. Okay, but it is not the case in the case of a realistic model. Okay. So the equilibrium refers to the forces on the tool chip interface and across the shear plane. Okay, so these are the some of the assumptions that what we are going to make in the shear plane models. Okay, then we move on to these slip line field models. Right. So, a line, the slip line field is nothing but a line which is nothing but a curved line, and also it is the tangential along the maximum shear stress. So there will be maximum shear stress along the shear plane. So I am going to draw a curved tangential line to that, and which is called as the slip line. A set of slip lines is called as slip line field. A set of slip lines is called as the slip line field. So this is normally is provided by, you can see a slip line border between the secondary deformation zone and the slip zone. It is called 45-degree angle. So we have two types of deformations. One is primary deformation zone and the secondary deformation zone. So that and all we will see, visualize later on. Okay. So these slip lines will be intersecting these free surfaces at a 45-degree angle. So Lee and Schaffer work is purely based on this slip line fields. So Ernst and Mech is for shear plane. For slip line, we will be dealing with the Lee and Schaffer. Okay. Then shear zone models. So this shear zone model is the better model than that of the previous models. That is the shear plane model and also the slip line models, because it considered all the features that is being neglected or omitted in the previous models. Okay. So in most of the models, we assume that shear stress on the shear plane is uniform. Actually, it is not. Okay. The stresses at the shear plane is not uniform. It will be varying. Right? And also we are going to consider that no strain hardening is there. Actually, in all the machining process, there will be a little amount of strain hardening. So now there are many studies, many excellent papers that predicts the strain hardening effect also during the machining process, during the formability. We can see the strain hardening factors and all. Right? So the friction among the interfaces is characterized by a friction factor or friction coefficient, mu. So mu is equal to F by N. So that and also we are going to consider in this shear zone models. But this friction coefficient is the strain hardening. It is not being considered in the shear line, shear plane and slip line models. So that's why we are going to consider this shear zone models. Okay. So shear zone models is associated with the Oxley. So I will tell you how to select these types of models while doing the simulation. You can see that particularly how this is being selected and all. You can just select that. So what are models we require? We can select. Okay, this and all, it is very general. So for what purpose this finite element analysis in manufacturing process is being done? The first reason is to validate the results, to determine the performance and effectiveness of the system. So how effectiveness the system is, that we are going to see. Then to identify the optimum conditions, that is what is the cutting speed, what is the feed rate, what is the depth of cut that produces lesser cutting forces, lesser interface temperatures. Likewise, we are going to decide, and also to reduce the production time and cost of final product, because most of the simulation studies will assist us in selecting a particular input values. So by this, we are going to reduce the manufacturing lead time. So various machining manufacturing process that can be modeled are turning, drilling, milling, then forming, then fluid flows, heat transfer, rolling. So these are all some of the machining manufacturing process that can be simulated. In drilling also, friction drilling also, it can be done using the softwares. Using softwares, friction drilling can also be done by using a blunt tool likewise. Okay. So categories of finite element models. So in the first slide itself, I have told there will be two conditions while doing a simulation study. The first one is the transient model, and the second one will be the steady state models. The steady state models will be available only after a particular value has been reached. Okay, so initially you can see, I'll tell a small example. Initially during the machining process, you can see the cutting forces will be shooting up sharply. After some period of time, it settles down, and that is the steady state conditions. The short rising of the cutting forces until it settles, it's called as the transient conditions. In the transient conditions, the values tend to change with respect to time. In transient conditions, the values will tend to change with respect to time, whereas in the steady state conditions, it doesn't change. So the steady state models represent a snapshot in time. The assumed chip shape is used. So this and all, we will see it in the simulation, real-time simulation. Then the shape may be modified. So kindly keep a remembrance of this. Assumed chip shape is used. The shape may be modified. We are going to do that modifications in our simulation studies. Then the transient models. So initially we are going to perform the study using the transient models. It tracks the evolution of chip geometry with respect to time. Right? So with respect to time, everything changes, and that is the transient models. So we are going to model the tool entry, the exit behavior, the chip shape, the contact notches. Okay, everything we are going to model. Right? The transient models. So unsteady chip behavior. This is what we are seeing. Unsteady big chip behavior, because it changes with respect to time. It changes with respect to time. Right. So in this unsteady chip behavior, we'll be having frequent remeshing. Why the remeshing occurs? Because material will be removed. And adaptive remeshing. So kindly take a note of this word, adaptive remeshing. Because in ANSYS and all, we will be doing the meshing, no? So the meshing that is adaptive. So automatically it changes the structures, and that is called as adaptive remeshing. The meshing will adapt so that it automatically remeshes once a new surface is being formed, and that is called as adaptive remeshing. So this is reaching steady state tool temperature is not practical without a special treatment. So what is that special treatment? We are going to remove some material from the chip, and then we are going to have a special shape on the chip, a special treatment on the chip and the special shape on the chip. So then only we can convert this transient condition into steady state condition. So it captures the steady temperature and chip behavior. So that is, it doesn't changes with respect to time. So these steady state models will not change with respect to time. So remeshing is not required, because once we have attained that steady state conditions, nothing is new surfaces are, even though it is being generated, okay, the same sort of values will be obtained. So frequent remeshings is not applied, because the distortion, you can see that distortion of elements will be less, because the distortion of the elements will be less in this category. So no special treatment is required, because the tool position does not change. Okay, so this and all we'll see. Then we come on to the 2D versus 3D models. So the 2D models are appropriate for orthogonal cutting simulations. Okay, so it can use only orthogonal. So while comparing with the 3D models, this 2D models computational time will be very, very less, but the accuracy of the results will also be less. For example, this 2D simulation can be done within 1 hour, whereas the 3D simulations can take until 8 to 9 hours. Will take 8 to 9 hours, the maximum, with a moderate meshing and element size. If I'm going with a further fine meshing, then it will be nearing to 12 to 13 minutes, 13 hours. So the 2D models are appropriate for studies, to study the fundamental behavior of machining process. The fundamental behavior, if I want to study, then I can go with the 2D models. So how the residual stresses, how the microstructural changes are going to take place, so that and all we can visualize clearly using these 2D models. So the 3D models are appropriate for studying the geometrical details of actual cutting tools. So how this cutting tool is going to wear, what type of wear is there. Okay, that and all we can easily visualize by using these 3D models, right? Because this tool wear and all, it cannot be easily seen during the 2D models. Okay, in 3D models only it can be easily visualized. But these 3D models require extremely higher calculation times. So that is the most important drawback of going with these 3D models. So historic developments I will skip down, because it's already time. It's already 10:50. So you can see it all started in the years 1980. I will rush up a little bit. So it all started in the years 1980s. So Shekunsky and Carroll defined the Lagrangian approach in the year 1985. So it has been only 35 years before only this simulation studies has been done. Okay. Then in the mid-20s, these automated remeshing techniques were introduced along with the Lagrangian simulations. So Lagrangian models. Okay. Then Chacon and Chenot uses this automated remeshing using the code Forge 2. Okay, which is being done at the French Research Institute. Okay, they are doing this automated remeshing strategies. Then Kamako, Mulrich and the Ortiz, so introduced a continuous remeshing techniques in the year 1993. So most of the developments of the simulation studies has taken place above 1990s only for high-speed machining. So the first deformed 2D models was introduced in the year 1996. So Carretti, Faulmuher, Wu, and Alton adopted the reinvesting procedure in the commercial software deformed 2D. So in the deformed 3D is also available. So these two comes in the same package. Okay. Then 1997 we have the Eulerian model. Then 2D simulations, planes. Then 3D. So 3D was introduced in the year 2000. You can see that. So before that it was only two-dimensional. So in 2000 only the turning process in 3D was first carried out by using the commercial software with automated remeshing, that is adaptive remeshing. By using the adaptive remeshing techniques, the first three-dimensional simulation was being carried out. Okay, so this and all I will skip it out. Right. This is very, very important. So in the machining process, normally we will be considering the Eulerian, Lagrangian, and arbitrary Lagrangian Eulerian. That is, considering both the advantages of Eulerian and Lagrangian, we are going to use this ALE software, ALE analysis. And normally we will be going with the ALE only because that is the best approach that we are having nowadays. Okay, so this and all I will skip because of the time limitations. The meshing. So the initial mesh is very, very significant for the results. So there are two types of meshes are available. One is fine mesh and the other one is the coarse mesh. So coarse mesh are used for testing. Okay, whereas a finer mesh is used for checking the model. So two different types of meshes will be used. So coarse mesh for testing and for validation, a finer mesh will be used, right? And most important thing is we are able to identify regions that are of more important during the simulation studies. So which area is very, very important in a turning process? The place where the cutting tool and the workpiece meets. The place where the cutting tool and the workpiece meets. So in that places, we are going to have a finer mesh. As we move away, we are going to have a coarse mesh. So that is the one of the beauty of this commercial softwares. So at the point of contact, we have finer mesh. Once we move away from that, we are going to have coarser meshes. Okay. So this is what we are speaking about. Okay, here you can see. So this is the primary deformation zone, the shear zone, the primary deformation zone. The secondary deformation zone is nothing but the point of action where this chip is going to slide over that tool. So here you can see the place where the tool and the workpiece meets. Here we are going to have finer mesh sizes. So once we move away, you can see the size of the mesh is larger. The size of the mesh is larger. So here also in the study also you can see. So this is called as the different meshings. So that is the beauty of this commercial softwares. So this and all will move. So material model. Right. So the material model is purely based on the flow stress equations. How the material flows, the flow properties of the workpiece material is going to have. The flow is nothing but the elastic strains, how it is going to behave in elastic and how it is going to in plastic conditions. It all depends upon the yield strength of the material. It all depends on the yield strength of the material, right? So that flow stress is very, very important, right? So based on that, we are going to have elastic plastic, elastic viscoplastic, then rigid plastic, then rigid viscoplastic, like this. Right? So we have two different zones, primary zone and the secondary zone. Right? In the primary zone, the temperature and the strain will be of different categories. In the primary zone, the temperature will be around 150 to 250 degrees centigrade, and in the secondary deformation zone, the temperature will be around 800 to 1200 degrees centigrade. And also the strains will be very, very higher strains. Will be higher strains. Okay. So what is viscoplastic? The mechanical response of solids that involves time-dependent irreversible strains. So time-dependent irreversible states, and that is called as viscoplastic. So these are the different models that what I am speaking about. You can select whichever model you like during the simulation. So Uzi model, Uzi metals model, okay, Oxley model we have, Johnson-Cook model we have, then Zerilli-Armstrong model we have. And normally we will be selecting this Oxley model and Johnson-Cook model. I will tell you how to select that. Okay, so normally we will be having the Oxley and the Johnson-Cook model. Then flow stress measurement. So how we are going to measure the flow stress requirement? Only from a tensile test. Only from the tensile test we can define this flow stress, but that is also a approximate one. Why? Because larger strains are going to occur. Larger strains are going to occur. So that is not possible with the real-time tensile test. Okay. So traditional tensile test involves measurement of the force. Okay. In normal conditions of machining, the strain rates that is at the primary zone is going to be 10 power minus 10 power 5 or 10 power 6. But in the real-time tensile test, we are going to have 10 power 2 only. Even in tensile or compression, whatever it is, we are going to have only 10 power 2. Where is 10 power 5 or 10 power 6 and where is 10 power 2? So that's why even the flow stress equations that what we are going to provide for newer material, if it is already installed, if it is already these metal properties are given in the software, then it is easier for you. But if I want to define a new material, then this flow stress equations has to be provided. So these values can be obtained only from the tensile test. Okay, the strain rates that what we are going to obtain from the compression or tensile test will be around 10 power 2, but that's a vast difference. So in that cases, we are going with a high-speed compression test, high-speed tensile or compression test. Even though we are going to with the 10 power 2, instead of 10 power 2 is 100, but only 450 per second we can increase. So 10 power 5 you can see how much? 1 lakh. So 450 is there, 1 lakh is there. You can see that much difference between. So that's why the flow stress equation that what we are going to enter will have to suit that real workpiece condition. So this and all I will skip that. So this is the friction models. The friction models normally we will be using the Coulomb friction. Mu is equal to tau by sigma. So tau is shear strength, this is the axial stress. So Coulomb friction models only we will be using. So this is the adaptive meshing. Here you can see in the simulation. So in the GIF animation, you can see the what if you can see nearby this. There is a remeshing that is occurring, and that is called as adaptive remeshing. So it is a remeshing technique where the distorted element will be substituted by a new one. The distorted elements, because the metal is being removed, so that is distortion. So it has been replaced with a newer material, and that is called as adaptive meshing strategy. So this and all, then I will move on. So this is what we are speaking about. So this is the 3D condition. So this is the cutting insert. So this is D-shape insert. Okay. So it has a nomenclature: DNMG, CNMG, SNMG, VNMG, TNMG likewise. 120404. That is the nomenclature that what we normally call these inserts. TNMG 120404. So likewise 160404. There are many nomenclatures. So this is the workpiece. So as you all know, the cutting tool will be in contact with the workpiece at a single point. So that point alone we are going to take for our material modeling. For our material modeling, we are going to consider. So this place we are going to have this. Okay, so we are going to remove material here. So this is for 2D. So this is for 2D. So we are going to be interested in this. Then we have the 2D simulation. We have different shapes. So this is a D shape. So here you can see. So this is the place where the cutting tool and the workpiece is going to meet. So this is made finer. Here also you can see this is made finer so that this place and this place will be in contact. Apart from this, we have coarse mesh. So these are the different tools that we have modeled for our studies. And this is the simulation that is being carried out. And this is the primary deformation zone. And this is the secondary deformation zone. You can see at the interface, the temperature can reach a maximum of 940 degrees centigrade at the secondary deformation zone. And normally it will be around 1000 to 1200. So in this case, it is 940. So at the primary deformation zone, it is around 400. It is around 400. Here you can see a continuous chip. Here you can see a continuous chip. So this is the stress where it is being acting. So this is the cutting forces where it is acting. So that can also be predicted using this. So this is the three-dimensional cases. So this is where the cutting forces. So as seen, you can see clearly how the shape of the tool and all is clearly visible. So if there is any wear, that is also visible in this cases. If there is any tool wear, that can also be clearly visualized. These are the cases you can see. So this is how the cutting forces or maximum principal stresses are going to act at the cutting edges and the places that surrounds the cutting edges, which supports that cutting edge, the edges which supports the cutting edge. From this also we can determine the effect of different cutting speeds on contact temperature. So by changing the cutting speed, how the contact temperature is going to change. So that and all we can see the mean stresses. So you can see here. So drastically it is going to rise. After some period of time, it is going to stabilize. After some period of time, it is going to be stabilized. If you have any doubts in this, you can ask me now. Or if you don't have any doubts, we will move on to the simulation studies. If you don't have any doubts, we will move on to the simulation studies.
Yes, sir. I have some query regarding this material model.
Yes, sir. Tell me, sir.
Yes, normally, sir, for material modeling, we normally use Oxley and Johnson-Cook material model.
Yes, sir.
And you are telling about this FEM modeling. So which
Yes.
one is better in both these? Whether
So
we choose this?
normally, in comparison with Oxley, they will be using only Johnson-Cook, JC model only, sir.
Yeah, of course, sir, of course.
JC Cook model only we can use, and in most of the research articles also you can see that JC Cook model only, because that provides better results than that of the Oxley model.
Yeah, sir. So now I'm asking the difference between this AVM modeling and Johnson-Cook modeling. So which one is better if you can tell me that?
It all depends upon the number of factors that we will be considering, sir. You can see that model also. I will tell you 1 second.
Yeah.
It will take only a little period time here. Right, here you can see Oxley. It's very simple model.
Yeah.
But here you can see the parameters, how much parameters. It all consider the temperatures, okay, the strain ordering coefficients, the stress values, it all considers that. So that's why when compared to Oxley model, this Johnson-Cook model is totally different. You can go
actually,
you can find it, the variations.
Yes, sir. Actually, Johnson-Cook is the modification of this Oxley model, right?
Yes, sir. Yes, sir.
Yeah, that's why I'm asking in between Johnson-Cook and your FEM. So which one is better if we'll do this modeling?
Johnson-Cook is better, sir.
Okay. That's how much.
Okay, sir. Thank you. Any other doubts to be clarified?
Sir, so this is Gopi Vel. Sir, how to ensure that whether our given meshing is right? How to verify?
So that's why we are told two things. For first time, if I'm going to do initial studies, then I have to go with the course one. For validation, we have to go with the final measures. We should have a trade-off, sir. Because if I'm going to increase the meshing size, then the computational time will also be higher, but the accuracy of results will be higher. So that is not needed in the initial cases.
Yes, sir.
Once we
Okay,
can see that this is the cutting cutting speed, feed rate, depth of cut that I'm going to use, then I can
Okay.
use different meshing sizes and I can find out the variation, and the best results can be, we can use that.
Okay, sir. Then, sir, if we using composite materials, then we need to give a different mesh size for particulate and matrix
No,
material, right, sir?
no. Only for material model we are going to divide.
Okay.
So that is, composite is a single material. We cannot use it as a different materials because the particles are embedded inside. No.
Okay. Okay.
I will come that on a Thursday.
Okay.
Okay,
Okay.
machining of
Okay.
composites. I'm going to handle. I will tell you the difference. Okay.
Sir,
Okay, sir. Okay, sir.
yes, sir. Please, one question.
Yes, sir.
Sir, can we treat this composite as an alloy during this material modeling?
No, sir. No, sir. No, sir.
No,
It
no.
is not be treated as an alloy, but we have to go with the tensile test first. In defining the new models, we have to carry out a tensile test. From the tensile test, the strain values that what you have obtained now for different times.
Yes, sir.
That has to be put as a input.
Okay, right, sir. Right. Thank you.
So the composites will behave differently because of the embedded particulates.
Yeah, correct,
So
sir. Correct.
it can be the output of the flow stress equations.
Okay.
If you're going to put that flow stress equation in the new material model, then you are going to model that composite in a better manner.
Okay, sir. Thank you, sir. Thank you.
Thank you. Any other questions? Or shall I move to the software?
Yes, sir.
Okay, sir. Okay, thank you. Are you able to see my window?
Yes, sir.
Yes, sir.
Okay, so the software that what we are going to see today is Deform 2D. Okay, so I'll be putting that in the chat box also. Deform 2D. So we have two for Deform 3D also, because both are licensed version. So we have to use only the licensed version. Okay, that is also available at a lesser cost also. So you can purchase for your own use or for your college use also, and you can produce a n number of papers, research articles in this. Okay, so here we are going to, because of the time durations, we are going to use only this Deform 2D. So first file, I will be moving a little bit fast, sir, so that they will share that recording session, then you can use it. Okay. New project. So new project, I will be giving it as AMAT, the name of the institution which is performing doing that FDP, AMAT. So the title, trial. So there are two unit system. Normally we will be using the SI unit, System International. So I am selecting that. Then next. Then operation 1. Here you can see machining transient. So now there is a drop down menu. Even though I put it here, no drop down is visible, because the drop down will be activated only certain amount of chip is produced. So keep it in mind. The transient to steady state is possible only a certain amount of chip is available during the study. So initially it will be only transient. Then next, so surface speed, meter per minute or rotational speed, you can give both. Rotational speed is n. Surface speed is v is equal to pi dn by 60 or pi dn by 1000, depending upon the unit. So I'm going to select this and I can give any values. Also you can use the same value. So next, the environmental temperature. Whether we are going with the hot machining or we are going with the normal machining or we are going with the cryogenic machining, you can change this temperature. Okay. Now the ambient temperature is 30 in our country, so I'm going to put it as 30. So these work interfaces and all, just to keep it as it is. Next, the temperature tool setup. The tool temperature is in ambient temperature 30. Then next, Then here import geometry. The geometry can also be imported from other modeling softwares, Pro-E, CATIA and all, no? From that also we can model the tool and the workpiece and then we can import. But here I am going to define as it is. So this is the cutting tool. So this is a portion. So there are 3 different cutting tools that is available, but I am sticking on with the normal carbide, right? So here I am going to put it as create. Here you can see this, a tool has been created. Now if I changes my values, what happens? Now I am going to change the nose radius as 0.4. You can see this, it has been changed now. So I am going on with the 0.2, right? So my nose radius I have set at 0.2. Create, close. So I have defined I have developed my material tool model. Then next, whether we want to provide any coating, because tools may also be coated and their effects can also be studied. In this case, there is no coating. So next, how much mesh size that I am going to provide? Someone asked, some professor, whether we want to go with the coarser or finer. In this case, I am going with the coarser because I am going to study how it is going to behave. So I am going with the least thing 100. Then I am going to generate the mesh. So here itself you can see the place of contact of the tool with the workpiece. It is being done in a finer mesh, and away from that it is a coarse mesh. Have you seen that? So this is the difference in meshing, because these places I am least important. I am going to provide least importance. So here only I am interested. And next, and next. Then insert a material setup. What is the material for this? I am going to import material. So this is the tool. Then for which I am going to produce the material as tungsten carbide. So my material is tungsten carbide. Tool material is tungsten carbide. Then next, so the workpiece is also a plastic. So the temperature is ambient temperature 30. Then next, then here also I am going to define the primitive geometry. Here also you can see directly we can change. So now I am going to change it to 2. So you can leave it as it is also. So first I will leave it as it is. Here you can see now I am going to change the value to 2. You can see the change. So whatever is your requirement, you can change. Then next, what is the size? The number of elements through uncut chip thickness. So this is the depth of cut. This is the depth of cut. I am going with the less depth of cut. So I can go with a higher depth, moderate depth of cut of 25. Okay. Now I am going to generate mesh. So this is the depth of cut. The number of elements through uncut chip thickness. So here you can see a finer mesh is being developed at the point where the cutting tool will be in contact. Okay, remaining places it is going to be bigger. Then next, workpiece material. What is the workpiece material? Now I am going to import, or I can create a new material. Someone has asked material name. Okay, I am going to give amateur. Define elastic properties. Yes, next. So flow stress equations, no? You can see. So someone is asking, no? So what is the flow stress equations? This is the Oxley. This is what is a Johnson Cook. Whatever it is. Okay, now you can select this. So you can see this. The strain rate, strain from the tensile test we can provide, so that it will take the material property. It will take the material property. Okay, now I'm going to cancel this. Now I'm going to import from the library. So steel I'm going to select, in which so here you can see AASI 1045. What is this? More. So here you can see. So this is a austenitic steel, pearlite martensite. The strain is 0.0 to 7. Strain rate is 0.1 to 10 power 6. Temperature is 20 to 130. The Young's modulus, everything it has been given. Now Next, I'm going to provide, here you can see J.C. Cook, Johnson Cook model. ERC is one type of lab. ERC is the name of the lab. Then,
Sir, your presentation is not working, I think.
sir,
Presentation is not working, I think so.
for the next model,
Is
it
it-
is not working. Yes, yes, yes.
Yeah.
The full thing I have to provide, I think so. Wait a second. Wait a minute. Wait a minute. Now it is popping out, sir.
Yes, sir.
Whether this is visible? Material
Yes,
is
sir.
right.
Window is
Yeah. Visible, sir, visible. Yeah, please, sir, carry on.
Doing it as amateur. Define. Next. So here you can see the flow stress equations. So which is appropriate for our study, we can select. Or here there is a booklet note that I am going to open. Here I am going to provide the strain rate and strain based on the tensile test result of that particular material, even for a composite material. Then I am going to provide apply and then OK. Okay, this is how we are going to define the new material. But now I am going to stay in with the library. So here it is the steel.
Sir, may I stop? May I ask something?
Yes, yes.
Sir, as you say that on the basis of tensile stress results, so first we'll have to experimentally do something. So find
Yes,
out
sir,
this.
yes, sir, yes, sir, yes, sir.
Okay.
For composite only. Because in
Okay.
here also we can have composite. I will tell you some composites, sir.
Correct, sir, correct. Please
So
carry on.
here, 1 second. Stainless steel, supralloy titanium, tool materials, aluminum also you can see. Beta materials. So no composites there. Okay. So for this workpiece material, I am going with the steel. In steel 1045, you can see the ERC with the trans data. So what type of data is this? I have to check with more. You can see the flow stress, the material, austenite material. Look at the strain rate, the temperature, Young's modulus, everything is being given here. The thermal. So these kinds of properties can also be given. I'm going with the next one. Here you can see the J.C. Cook, the Johnson Cook model, middle flow model. Then 1045 ERC, you can see. 1045, you can see. Fracture model is also there. Fracture model is also there. Okay. Here you can see the Oxley equation. Here you can see the Oxley equation. So which model we require? So that can be selected. So now I'm going to load this. So here you can see Oxley equation. So the flow stress equation that what I have selected is Oxley. If I want to select J.C. Cook, then I have to go with the ERC data. ERC is a company name. Okay. Next. Then you have to position that, no? So generate default position. So the default it will be positioned. The problem will be with the 3D only. 3D only we have to manually position. That is very, very difficult at the initial time. Once you learn it faster, then it is very, very easier. Then next. So Uzi tool-wear model. So you can, from literature survey, you can study for this material, what is the parameter values for Uzi tool-wear. Okay, this is the equation. So A and B only we have to provide. Okay. Next. So number of simulation steps, I am going to limit it to 100. And number of increments to save, 5 increments to save. Length of cut, whether I want full or any off, I am going with off. Okay. Next. So status is ready. Check data. Once we get check data, you can see on the lower left corner, something will be running, and finally the database can be generated at blue. Once this blue is available, then only I have to click generate database. right? Now there is no red. The left bottom, you can see done writing database. So next, do you want to close current operation? Yes. Then simulate. There are 3 tabs now: pre, simulate, and post processing. Pre-processing, simulation, post-processing. In simulate, run simulation. The simulation has been submitted. So the simulation graphics also you can see. The simulation graphics also you can simultaneously see. You can see 57, step number 57, the temperature. What is the temperature here now? Is it visible? The temperature is 261. You can see 57 steps was completed. 80 steps completed. So what is my temperature here? 369. Clear? Right, now the simulation has stopped. Why it has been stopped? Simulation is completed and stopped at the user specified time step. I have provided only 100 steps. So it has stopped. Okay, now consider this one. I have done some previous study and now I am going to load that, okay, because it will take some time. I don't want to take your valuable time. So this is the case, okay. So at the final you have seen that. So here there is a problem in this because I have changed the material. Instead of 2 material, I have given it as a workpiece material, so temperature will not change. Here, the state variables, no, you can see what is the temperature, then what is the deformation, so this is the temperature and this is the deformation, that what you have studied. Okay, this is the case. Now we have completed the transient conditions. We should not take the values. So kindly accept, we should not take the values. Then what we have to do? Then once again I have to go back to pre. Once again I have to go back to pre. I have to select some values before. So totally it is going to be 750, I think so. So I go to select, here I am going to select now, you can see 755, 752, 550, 72, like this. Okay, now I am going to select this step. It should be in positive, 565. Now, delete operation, add die stress. Now I am going to add operation. You will lose steps after step 565, yes. Now you can see this type now, initially it is not activated, now it is being activated. That is, once a pre-quantity of a chip is being produced, this will be converted into steady state. Now I am going to do this machining in steady state. Open the operation. Okay, now it is in the steady state. Next, you can see the tool has been gone. Why? Because previously I have told, for steady state condition, the chip shape has to be changed. Some modifications has to be changed. Now I am going to select this to this. Okay, sorry. So this is the selector. Now from this to, so start now, start to end. So these nodes I have selected. Why I am going to select? I am going to remove this so that a free surface is being developed. So that's why I'm going to convert the transient into steady state. You can tell me one important thing. What happens when I select from shear? Okay, so I'm going to cancel. Now I'm going to select from shear to shear. What happens? You can see everything is being selected. Why? Because this is the place where it comes through the tool. So it has to be only from this side. So from shear to here. So this piece I am going to remove. So you can see the number of nodes is 10. Next. So that will be removed now. You can see that. That is being removed. Now I am going with the 10 simulation steps. Next. Check database. On the left side you can see database can be generated. Generate database. Done writing database. Still now there is no problem at all. Next. Do you want to close the next current operation? Yes. Then open the simulation. Now run the simulation in the steady state conditions until the steady state reaches. There will be some problems. Here you can see steady state solution has converged. Steady state has been converged. Within one step, the steady state has been converged. Then post. Now look into the temperatures. Because as I previously told, because I interchanged the material, okay, the temperature is not coming. Okay. This is the temperature. This is the pressure, you can see. So I can go with the local or whatever it is. Then this is the displacement, the velocity, this is the effective stress, effective strain rate, effective strain, damage, whatever it is. Okay. Now I want to determine the cutting forces. How to do that? So now the steady state has been reached. Now I want to determine the cutting forces. Kindly be with me for the next 5 minutes. I will finish it as early as possible. Now 1 second I am going back to pre. 1 second I am going back to pre. Okay. So after steady state is reached, now in the pre-processing you can see add die stress. Add die stress. So die stress. Next the material. Next number of the extra die components. There is no extra die components. Next data stress is isothermal. Next, next, next. Click just next. Now interpolate forces. That's all. The forces have been interpolated from the workpiece to the die. Effects in the workpiece, the force in the x direction is 0.0043 newtons, and here also the same case in the die. Fi also the same thing. Okay. So this is how you are going to interpolate the forces. So cutting forces can be interpolated. The interface temperature can be interpolated. The pressure, the strain rates, pressure, whatever it is, we can interpolate from these studies. So this is all about this. So here you can see how the cutting forces are going to act. So higher, that is red color is higher, no? So higher cutting forces is acting exactly at the contact point. As we move away, the cutting forces are lesser. During that, the chip is going to slide over the rack face, no? Here the cutting forces is also higher. But here you can see, this is the place which is not going to be in contact. So the cutting force is less here. So higher, then it reduces. Do you have any doubt in this?
Good morning, sir. I'm Ram Gopal Reddy.
Good morning, sir. Tell me, sir.
So, is there any criteria to choose the type of model, sir?
So, different models produce different results, sir. First one thing.
Okay.
Okay, that's why for ASA 1045 itself, we have both the Oxley model and Johnson-Cook model.
Okay.
Right? So the behavior of the material, because there are variations in material itself, batch to batch variation, within piece variation, piece to piece variations, we call it as. No two different materials will be the same. So materials, the same materials will be different. When you test for a harness, at different places will be having different values, no? Similarly, no workpieces will be the same. So it will produce different force stresses equations. So in that cases, you can select whether it is a Oxley or Johnson-Cook. But most of the cases in the simulation studies, we are using only JC-Cook, the Johnson-Cook model only, because it is the superior than that of the Oxley model because of higher parameters that it is going to consider.
Okay, sir. Sir, one more question. So how to incorporate minimum quantity lubrication in this model, sir?
So that and all, we have to use the heat transfer coefficient during that model, no, sir. Third step, you can see. Heat transfer coefficient. So that we have to study and then we have to provide that, sir. We can do that in hot machining and all, we can increase the temperature, ambient temperature. For example, if we want to heat the cutting tool or the workpiece to 80 degrees centigrade, then the temperature of the workpiece can be increased to 80. If it is the cryogenic temperature, then minus, we can put it out. But for MCQs and all, the convective heat transfer rate, that and all we have to change. That will depend upon the material and the coolant that you are going to supply.
Sir, what is the cost of this deform, sir?
So it will come around 50,000 rupees, sir, one single license.
Okay. Thank you, sir.
Thank you, Professor.
Yeah, sir, I have one question.
Yes, sir, tell me, sir.
Yeah, thank you for sir for your nice presentation.
Thank you, sir.
I want to ask the one question because I am also using 3D, deform 3D, and I'm also a manufacturing. I have did my Ph.D. in machining of hard materials. Right.
Okay, sir.
So that's why I'm asking some questions because as we do these kinds of simulation with the help of this deform 3D or 2D. So right now these are not being acceptable in the research market. You can see when you are going to present some paper by using these kinds of software. Suppose
no, sir. They are accepting, but only simulations they will not accept.
Yeah, we require some
novelty. Yeah. There should be some novelty in your design.
Yeah, definitely, sir. Definitely.
Not only in your material, the way of coding or the way of simulation that what you are going to present.
Means there are some
software nobody will accept.
Yes, sir. Actually, there are lesser rate of accepting these kind because I'm also doing some work in these kinds of software, right? Okay. That's what I'm asking. And because as compared to this deform 3D or 2D, if we are doing some modeling with help of this empirical modeling and this analytical model, these are being accepted as compared to these kinds of software, right?
Yes, sir. Yes, sir.
So I'm just asking, what is the difference between these two? If is there any chance if we are doing some work on this using deform 3D and 2D? By accepting these papers, what we can do, sir?
From 2D or 3D, whatever it is, what is your net result? So the simulations can be used for optimization only, sir.
Yeah,
so before going for an elaborate study, the initial studies we are going to compare the results obtained from the simulation and the results from the experimental. Finally, we are going to compare and you can tell the nearby values. So accurate values will not be provided by the software, only nearby approximation.
Right.
In simulation itself, we can see nearby approximation only we can provide. Exact conditions will not be provided. So knowledge how that thing is working, that and all we can tell. But part of that your research article should be on simulation, not on free.
But sir, if I tell you about my experience regarding this one of the reviewers of a good journal, he gave me the comments that these kinds of software that is deformed 2D or 3D, these are normally used for the deforming purpose. These are not for cutting machining of materials. So
it all depends upon the reviewer, sir.
Yeah. That's what I'm asking.
It's a simple thing. It's all depend on the reviewer.
Yes, sir. Anyway, sir, very nice explanation. Thank you very much, sir. Thank you.
Thank you, sir. Thank you.
Okay.
Any other queries, sir?
Sir, good morning.
Sir, good morning, sir.
Sir, is it possible to use this software for unconventional machining process, sir?
Unconventional machining, no, sir.
Okay, sir. Sir, please suggest any other software to use unconventional machining software, sir.
So unconventional, they are using Abacus, sir. Abacus they are using, sir.
Sir, in Abacus, all types of unconventional machining process is possible, sir?
That I am not aware of because I have not gone to that yet. Because we are doing only traditional machining process only through the softwares. And also we have another software that is called as Advantage. That is also specifically for traditional process only.
Oh, okay, sir.
Because unconventional machining process, there is no specific softwares, but we can do that in Abacus. But the knowledge level should be higher because there should be very good knowledge, working knowledge in Abacus. Then only we can do that, sir.
Okay, sir. Thank you, sir. The session was wonderful, sir.
Thank you, sir.
It was very useful, sir.
Thank you, thank you, thank you.
Yeah, thank you, sir.
Any other queries, sir? Tanigacham, sir?
Participants, do you have any queries, any doubt? Today, resource person will come to join another 2 sessions, sir, for different topics. If you have any question also, you can interact later. Shall we conclude, sir?
Yes, sir.
Okay. Thank you, sir. You have given a wonderful lecture on machining simulation.
Thank you, brother.
In simulation, we need hands-on experience, but through online, it is very difficult to 100% explanation. But you have done a wonderful job, sir. Thank you.
Thank you, brother.
Thank you, sir. Thank you, sir. Thank you, sir. Sir, I want to take screenshot. I want to take the screenshot. Only 1 minute. 1 minute.
Yes, sir.
Thank you, Professor. We will meet next.
Thank you, sir. Thank you, thank you, thank you.
Okay, thank you, thank you. Participant, the feedback link is shared in the chat box. Kindly fill it up. See, in the Google Meet, there is a restriction. 100 participants. Last week, we rectified that problem. But today, the permission is not given. We asked the permission may be granted within today. Thank you.
Okay, sir. Thank you very much, sir. Tani, sir.
Thank you, sir. You are very good interaction, sir. We are expecting more from other sessions.
Yeah, sir. Really. Thank you very much, sir. Thank you.
Thank you, thank you, thank you. Participant afternoon session start at 1:45 p.m. One of the important topic, composite in the area composite. Come to join as early as possible.